I know it does that tick tick thing, but then it does this, and I don't want it to do that. All right, here we go, guys. So we started yesterday with doing a few of these examples. The first couple are pretty straightforward. I went through and I highlighted all of the conversions just so they're easier for us to see. With this first one, it says how many centimeters are equivalent to 3 meters. So the way that we solve this is we write down the thing that we know are 3 meters. Then we use our conversion factor to solve and find how many centimeters, which is what we're actually being asked. We make our conversion factor with this highlighted portion here. If we know that 100 centimeters is equal to 1 meter, then that means that because these two things are equal to each other, if we divide one by the other, it's the same as using the value 1. So that's why these two things are equivalent to each other. So here I'm going to put the units that I want to get in the numerator, the things I want to get rid of, the units I want to get rid of in the denominator, and then fill in my values, 100 centimeters per meter. So we know that 3 meters equals 300 centimeters. Any questions? Straightforward, right? You guys have done this before. The next one, we're going to go the other way. We're going to start with 45 centimeters and figure out how many meters we need to calculate, or we get from that. So the same thing. We need to solve this for meters. The thing we're going to solve for goes in the numerator. The thing we're going to solve for goes in the denominator. And we find if we do the math on these numbers, centimeters cancel. We end up with 0.45 meters. Everybody get them all right so far? 100%. Okay.
Yeah.
I just grade for completion, so you guys are all right. All right. So number 3. This one might remind you more from chemistry from last year. 1 mole of water is equivalent to 18 grams of water. If a glass of water has a mass of 200 grams, how many moles of water is this? We're going to use the same process we used up here. We start with our 200 grams, and we're going to use our conversion, moles per gram, to figure out the number of moles. So here, we're told that every mole of water is 18 grams, so 1 mole divided by 18 is going to give us, I did this one earlier, otherwise I just pull out my calculator. I got 11.1 moles of water. Any questions? So far, so good? All right. So now we're going to switch pages and go to problem number 4. Alrighty, so problem number 4 has a bunch of metric prefixes up at the top. Refocus that. The radius of the Earth is 6,378 kilometers. What is it in meters? You might be able to do this one in your head. So we've got 6,378 kilometers times, and I'm converting this to meters, so what I want goes up at the top. What I'm canceling out goes underneath. For every 1 kilometer, there's 1,000 meters. This is a mistake that I see students make sometimes when you're doing these from memory, is they want to say that kilometers is bigger, and so they want to give it the larger number. But you want to make sure that whatever the smaller unit is has the larger number of those units. So this is going to have 1,000 of the smaller things and the one bigger thing. And we cancel kilometers, and now we've got 6,378,000 meters. That'd be a long race, right? Sam. Oh, you were right. So we were given the radius, and we have to find the diameter. So what do we have to do? Divide by 2. Multiply by 2. Right? So we're going to take 6,378,000 meters times 2. I can't do that in my head. Quickly. You guys got it, don't you? I can hear you guys saying it. 12,756,000 meters. Better? Yeah. Thank you. Okay, now I'm going to be all nervous about that. Nobody caught that in first period. I know, right? In an experiment, you find the mass of a cart to be 250 grams. What is the mass of the cart in kilograms? Is this going to be a number bigger than 1 or smaller than 1?
Smaller.
Smaller, yeah. So I have 1,000 grams in every kilogram. So 250 divided by 1,000 is going to give me 0.25 kilograms. All right, next one. How many megabytes can fit into a 4.7 gigabyte DVD storage? So here's our comparison between gigabytes and megabytes. And when you look at these, a gigabyte is 1,000 times larger than a megabyte. So we're going to need 1,000 megabytes for every gigabyte. So I'm just going to write this down here. 1,000 megabytes equals 1 gigabyte. I remember, by the way, my first computer, our first computer, the hard drive was, I think it was 250 kilobytes. It was very small. I know, right? that was in the mid 90s though. Anyway, yeah, we got our first computer when I was a sophomore in high school. Okay, so we've got 4.7 gigabytes, and we're going to convert that to megabytes. So we're going to have to multiply that times. For every 1 gigabyte, we have 1,000 megabytes. So that's going to be 4,700 megabytes. Keep this one. Any questions? Okay. Last one on this page. A mile is farther than a kilometer. So if you think about a fixed distance, like the diameter of the moon, would the number that expresses that distance be larger in miles or kilometers? Would you have more miles or more kilometers? You're going to have more kilometers. You're going to have more of the smaller thing. So if you were to look at a distance between 2 points, if your measurement is large, you're not going to have as many of them as if it's small. That's all that we're saying there. That's another way to think about it. I usually have a visual image like this in my head when I'm thinking about stuff like this. I actually lay out the rulers on the floor. Okay, on the back. So $1 is equal to 0.73 euros, 73 euro cents. Which one's worth more, $1 or €1? Can you tell from just looking at the conversion? Yeah, a whole euro would be worth more, because if we had a whole €1, that's going to be more than $1. So that's one way to think about that. And then how many dollars is €1? If we start with €1 and we multiply that by this conversion, for every 0.73 euros, we have $1. That's going to give us $1.37. It's kind of a lot more. I went to France and Belgium with my husband once, and we had one day where we needed euros and we had dollars and we had $100. So we took the $100 to go exchange it for euros, and we got 40 euros for $100. And then we were like, well, this isn't very many euros. Where are we going to eat lunch? Being Americans, we were like, let's go to McDonald's. That will be inexpensive. It cost us 25 euros. Yeah. So our $100 was reduced to lunch at McDonald's and 15 euros within an hour. Oh, it was harsh. Okay. Our next one.
Yeah, $50 in McDonald's?
25. Well, 25 euro.
So
Yeah.
like
More than
Yeah.
$50.
Yeah. I know. But that's because when you convert money, they charge you for that. Like, that's a service you have to pay for. Ugh. Anyway. Yeah, we were hoping for like 60 euros, not like 40. Okay, so number 9. And this one's where it gets a little bit tricky, right? In 2012, Germans paid 1.65 euros per liter of gasoline. At the same time, American prices were $3.90 a gallon. You look at this, the larger number is the euros, or the gallons, right? The dollars per gallon. But in euros looks much smaller. So we're going to investigate this a little bit. How much would a gallon of European gas have cost in dollars? All right, so we're going to start with the European price here. If we've got 1.65 euros for every liter that we purchase, we need to convert this so that it's dollars per gallon, right? We want to know how much they would pay per gallon if we were comparing it to our rates. So first, I'm going to convert this to euros. So I'm going to have 0.76 euros per dollar, right? And then euros will cancel. Now I have dollars per liter. Now I need to change it to gallons. So for every 3.78 liters, I have a gallon. And, whoops, I'm going to keep dollars. Get rid of this, get rid of this. I'm going to keep dollars, I'm going to keep gallons. And if I used a calculator to calculate this, I would end up with $8.21 per gallon, right? And that is a lot more than we pay here in the States, right? What's the big difference between those? Do you guys know? There's a difference in the way that they collect taxes to work on roads, mostly. And so this way, if you tax gasoline, you're actually having the people who buy the gas pay for upkeep and maintenance of your roads, which is kind of a smart thing to do because the people who are actually using your roads then are the people who pay for them. But it's a philosophical difference, but it makes gas cost more. So that's part A. Part B says, how much would a liter of American gas cost in euros? So we're going to take our $3.90 a gallon American gas. So we've got dollars per gallon. Convert it first to euros. Whoops. 0.76 euros per $1, which is going to allow dollars to cancel. And then we have to convert liters and gallons. So for every 1 gallon, we have 3.78 liters. So that, when we calculate it out, is going to be 0.78 euros per liter. So keeping liters in euros. So that's about half that price, right? It's a lot less. So our gas prices aren't terrible, but we fund some of our costs of driving other ways. You guys have any questions about number 9? One thing I like about number 9 is it's the first time on this page where using multiple conversion factors really helps you save some time and keeps things a little bit simpler. I mean, this wasn't the smoothest thing for me. I wrote some things wrong here, but when you set it up this way, it's a little bit more difficult to make a mistake than if you're using other kinds of proportions, or you're doing equalities where you're setting two things equal to each other. Just because it's a little bit more straightforward once you get used to it. Okay, the next one. This is a fun one. A mile is equivalent to 1.6 kilometers. If you're driving at 60 miles an hour, what's your speed in meters per second? This is a lot of things. If you are a runner, you might be interested in this kind of problem. So we start with 60 miles per hour. First, we need to convert it to meters. So for every 1 mile, you have 1.6 kilometers. For every kilometer, you have 1,000 meters.
Can you clear the notification?
Yes, I can. Sorry about that. I didn't see it. Okay. All right, so we've got 60 miles per hour, 1.6 kilometers per mile, so miles will cancel. 1,000 meters per kilometer, so kilometers cancel. Now we're at meters, which is one of the things we wanted to keep. Then we got to convert hours to seconds. So for every 1 hour, we have 60 minutes, which which allows hours to cancel. For every 1 minute, we have 60 seconds. So minutes cancel. And so you can see that by the time you're at the end, you only have one unit left on the top and 1 unit left on the bottom. If you do all the math, you should end up with 26.7 meters per second. You guys have questions about that one? Does this make sense? Thumbs up. Okay. Okay. All right, back page. It's going to get a little bit more abstract here. All right. So now what we're given is some mathematical relationships. We're given some equations, and we have to think about what happens to the value of y. So each of these has 3 variables, y, k, and x. K is a constant, so it's just a number. And then we have y and x. So what we're being asked to do here is if we make a change on the right side of the equation, how will the value on the other side change? So another way to think about it is what do we have to do to the other side so that they stay equal? So if we change this so that x is tripled, this would be k times 3x, right? What would we have to do to the value of the other side? I think I heard it out there. We have to multiply it by 3, so we'd have to have 3 times y. So what we would have to do, I'd have to, let's see, the value of y is tripled. So if x is tripled, then y is tripled. You guys have questions about that first one? You see what we're doing? We're trying to make them equal on both sides if we're changing one side in some way. For letter B, if x is halved, so it's half as much. This one's tricky. If that has to be x over 2, right? If you divide k by x divided by 2, this is equivalent to k times 2 over x. You guys remember that from algebra? So what that means is what we've done here is we have 2 times k over x. So what has to happen to y? If you multiply this side by 2, then you have to multiply y by 2. This is because this is an inverse relationship. If you're looking at the denominator and you make it smaller, then y is going to be larger by that factor. It gets a little bit more complicated in C. What if you double x? Then what happens? All right, so I've got k and then 2x squared, right? So I'm going to see what happens here. K over 4x squared. So if I want to compare that to what I started with, it would be 1 over 4 times k divided by x squared. So what actually ended up happening, is when I doubled x, I actually multiplied that side of the equation times 1/4. So that means on the other side, I don't know, sometimes I say y is quartered, but that doesn't sound correct to me. Yeah, so I'm going to say y is multiplied by 1/4. I think that one's actually the hardest one to think about. All right, last one. It says y is equal to kx squared and x is tripled. So here, instead of having x squared, I have 3x squared, which means I've got k times 9x squared. So what's happened is this side of the equation is 9 times larger. So that means the y has to be multiplied by 9. You guys have any questions about that section? I know it's a little bit different. Okay, so the number 12 says, well, one variable is directly proportional to another. Doubling one variable also doubles the other, so the same thing happens to both sides when they're directly proportional. If y and x are variables and a and b are constants, circle the relationships that are direct proportions. For those that are not direct proportions, explain what kind of proportion does exist between x and y. So this is going back to that handout sheet. You guys remember this? So this one is directly proportional. This is no relationship. And these have different relationships. So we have inversely proportional, proportional to the square, and the square of y is proportional to x. So there's different ways you can approach this. If you look at this and you have something that's in the form y equals mx plus b, this is directly proportional. So if you don't have anything with squared, if you don't have anything with exponents, if you don't have anything where you have a variable that's in the denominator of a fraction, it's going to be directly proportional. All right, so who thinks this one's directly proportional? A. Yeah, this one's directly proportional. What about B? Yeah, that one's directly proportional. What about C? Yep, that's proportional too. They didn't tell us what the slope was, but it's 1, right? It's not given. What about D? Is that directly proportional? All right. So this part D is not proportional because x is squared. So part D is not proportional because x is squared. We can refer back to our charts. And we can actually look all the way over here to figure out where it should go. It looks a lot like this, right? Y equals ax squared. So we would say that this is proportional to the square of x. All right, what about y equals a over x? Proportional? No, not proportional. If we look at our chart, y equal, where to go? Yeah, a over x is going to fit with this, this representation. So we're going to say that this one is inversely proportional. I'm just going to write inverse. What about f? Proportional? Yes, that one is proportional. G. G's like E, right? Those two are similar to each other. So this is another inverse. What about H? Is that proportional? Proportional? No, this is y is inversely proportional to the square of x. Whew. That's complicated. You guys have any questions about that section? No questions? All right, last bit. All right, so there's a bunch of lines here, right? It says which ones are linear. Which ones are linear? So those are pretty easy to pick out, right? Anything that's a line that's not a curve should be linear. So this one, this one, this one, and this one. All right, so it's going to be B, D, E, F, and all those are somewhere in the form of y equals mx plus b. Right? If we made an equation, they would all fit that form. Which ones are direct proportions? All of them? What's the difference between a line and a direct proportion? What has to be true? Proportions. That's a good question. Yeah.
Don't they all have to be like ascending instead of descending?
Not necessarily, but they might. Yeah. They have to go through the origin. So they have to have an intercept and y equals 0. So, Ethan, your comment, the ascending or descending, it can be descending as long as it was in either of these quadrants and still go through the origin. So yes, but only in the first and third quadrants. So the only ones that are direct proportions are going to be B and E. And then which ones are inverse proportions? So inverses are, when it's a slope and then 1 over x. So which ones does it do that? Do any of them do it? A does it, yeah. I'm going to color that one a different color. So this guy does that. You guys have any questions about anything on those worksheets? Okay. You guys did a super job today. We got all of our stuff done. Keep it up.
Yeah. So did we just go over like what we did yesterday?
You should have done that on Tuesday.